Good morning, everyone, and welcome to the IBM Qiskit Live Quantum Seminar Series. In just a minute, I'll be thrilled to roll out this week's seminar with Dr. Ali Javadi. Before we begin with introductions, first let's give everyone a minute or two to tune into. And as you know, this is a very special seminar. This is the 100th Qiskit IBM Quantum Seminar. So with that, folks, before we even get started, first, let us know, as always, where you're tuning in from, to which you can do in the comment chat box on YouTube, above, left, right below, somewhere on your screen, the usual place. And also, I'd like to share some thoughts and comments on 100 episodes of the seminar and some of the origin of it. First of all, I'm glad to see so many of you returning every week, a lot of familiar names. But it's good to remember that science, education, and even growth thrive on exposure to new ideas, fresh discussions, unexpected questions. These are the key ingredients that fuel our quantum community. As you remember, in March of 2020, and I don't need to remind anyone what happened, drastically things changed. This is exactly where this seminar was born. And now, in anticipation of the 100th seminar, it's good to take pause and look back. I think at that time, most of us, including myself, were torn from our usual connections, that usual rich exposure to different ideas and visitors and visits and other friends and scientists, colleagues, friends, and beyond. We lost that ability to easily connect with other researchers, to go and tackle bigger challenges. Carl Jung, I think, put it well. The meeting of two personalities is like that contact of two chemical substances. If there's any reaction, both are transformed. So at that time, we asked ourselves, how can we take this upending negative into some kind of a positive? Can we actually use this moment to maybe change up the way we've been used to communicating and exchanging ideas, greeting, meeting each other? And that's the origin of this seminar. We got busy, very busy, in about 2 weeks, which is, I think, a record time for kicking off any kind of academic flavored seminar. We were able to kick off the very first episode with the Qiskit community team. And 100 episodes later, 2 years, to which I think we're all very pleasantly happy to see all the progress. The results have surprised us. You guys have watched over 250,000 hours. That's 250,000 hours of total watch time. That's about 130 years of a person's work life. That's a lot. About 1 million different viewers who've tuned into the seminar, over 26 million impressions. It really goes well beyond what we could have imagined at the start. And we're happy that we have been able to hear all kinds of stories, people finding their PhD dissertations, finding their PhD advisors, topics of passion that they've linked up, folks forming connections on the seminar, through the seminar, and the ability that each seminar reaches on average about 8,000 to 8,000 people or viewers. Compare that with the usual thing we're used to in a university academic seminar, we get 20, 30, maybe 50 folks. So we're really happy to have many great comments, and I already saw some comments from folks here. You can even see here today we have folks from Chicago, Israel, India, New York, Bulgaria, Brazil, Germany, Taiwan, China, and the list goes on and on. So really thrilled. I want to thank you, each and every one of you, for tuning into this seminar, as well as to also thank our AV team, Clinton Herrick, David Rodriguez, Paul Searle, everyone else who's contributed, our various hosts, Olivia, myself, Cetera, who's helped us, and all the people on the back end that you don't always get to see, who really help make this run smooth, and 100 seminars. So with that, I'll remind you that this seminar takes place every Friday at noon Eastern time, and will be hosted here, but you can only go back and rewatch. You can only ask questions live and interact with our fabulous speakers during the seminar itself, which is now. So with that, and without much further ado, let's dive in. Today, I'm thrilled to roll out the 100th IBM Qiskit Live Quantum Seminar Series dedicated to you, the research and academic communities. I'm your host, Zlatko Menev from IBM Quantum Research, and today I have the special personal pleasure and privilege of hosting Dr. Ali Javadi from IBM Quantum. Ali will speak on scalable, abstractable, retargetable, and pluggable compilation, something that's very essential for quantum computers. Before we bring Ali, let's give a bit of a bio. Ali is a principal research staff member at IBM and a technical lead for IBM's quantum software and compiler. Ali received his PhD in computer science from Princeton University in 2017, and Ali leads the compiler subthrust of the Co-Design Center for Quantum Advantage, C2QA, and is a visiting lecturer at Princeton. So with that, Ali, it's a real pleasure to have you here on the 100th Qiskit Seminar. Welcome. How are you today?
Hi, Zlatko. How are you? Thanks for inviting me.
All right. Well, it's our pleasure to have you, Ali. I think at this point, I will turn it over to you, and the stage is yours.
Okay, so you see my screen? My screen is visible? Sorry.
Yes, it is.
Okay. All right. Thank you again, Zlatko, and everyone on the Qiskit Seminar Series. Sorry.
Ali, before I actually let you go, we already have a question which I forgot to answer. The question is, was the raffle done already? There was a raffle here for announcing the winners of a special session, and I'm sorry I should have mentioned this, where you get to have a fireside intimate chat if you want with Dr. Ali and myself, where we can talk about anything quantum computing related and so on. This will happen after this seminar. I believe we'll announce the winners at the end of this call or by email. So keep an eye on your email to see if you've received the invitation. And at the end of this seminar, we'll announce the winners. So with that, Ali, now the stage is yours.
Okay, thank you. Yeah, I mean, I must say it's a real pleasure to be here. And it's really incredible to see 100 episodes of this seminar series. I mean, I can't say I've watched all of them, but I've watched a good number of them, and I've learned a lot. So it's an honor to be invited here for the 100th episode, and I hope I don't disappoint. Okay, so for this 100th episode, I was basically invited to talk about Qiskit itself. I decided to sort of mostly focus on one central part of Qiskit, which is a compiler. But before getting into all of that, I thought I'll give some bigger picture, some background history about Qiskit and where it started, and sort of how it plugs into the broader ecosystem of quantum computing. So let me share. It's full screen now, yes? Okay.
Now I see full screen. Perfect.
Okay. So Qiskit was released you hear me now? Sorry, I think I got muted.
Yes.
Okay. So keeps mute. Okay. I think I might need to take this off. Sorry.
All right. No worries, Ali. This is always go ahead. And now we have you muted, so no worries. We'll get you unmuted, and then we can hear you. I see your mute icon, Ali, is on. It says that maybe we need to change your mic, so okay. There it is. Now we hear you.
You hear me now?
Yes.
Okay. Okay, so I wanted to give a little bit of a background about where Qiskit started and where it is now and where it is going towards. Basically, so Qiskit was started as a kind of a small project within IBM a few years ago into 2017. So this is a screenshot I took of one of the first releases. The very first release was kind of empty. So this is the second release, which is like, you see, like it had the first introductions of it, like a quantum circuit and like basic mapping to hardware. And also it had this interface to the IBM quantum experience at that time. So this was, I mean, for folks that don't remember, this was in 2016. IBM quantum computers became accessible over the cloud. And so for the first time, you could basically just, even if you didn't have access to an academic lab or anything like that, you were able to execute, small quantum experiments and actually like quantum programs. So as part of that first release, I was digging through that. There was this tutorial about playing the CHSH game on an IBM quantum computer. So, you guys might be familiar, everyone in the audience, that the Nobel Prize in Physics this year was awarded to a few experimentalists in the 1970s, 1980s, 1990s, did some seminal experimental demonstrations of violations of Bell's inequality using things like the CHSH game. And here we are in 2017. You can basically do similar experiments, of course, not with the whole detail and the loophole freeness of it, but still, like you're able to connect to a quantum computer over the cloud, write circuits, execute them, and see this the quantum mechanics in action. And this was, kind of nowadays it's taken for granted that you can do this, but I think for folks who remembered at that time, maybe 5 or 6 years ago, it was a real. I just remember the first feeling of executing a program on a quantum computer and getting results back. It was kind of incredible. So yes, that Qiskit started. This is Jay Gambetta doing the commit of releasing the package in 2017. So it was basically, I think, Jay and Andrew Cross, Ismail Farrow, Lev Bishop. So it was a small project. But then fast forward to now, it's really grown. So Qiskit now consistently gets about over 100K downloads per month. It is used by over 800 other packages that are built on top of Qiskit. Just to the core part of Qiskit, which is called Qiskit Terra and on GitHub, it is 400 unique individuals have contributed code to it. It's like over 2,000 people, almost 2,000 people have forked it, et cetera, et cetera. So it's a really growing project. But also, I just wanted to sort of now go into why the project was started and like sort of how I see it within the broader landscape of quantum computing. So, basically, to do quantum computing, it was realized early on that we can do certain things that are interesting from an algorithmic point of view. But we need, for the two ingredients that we need for them are qubits. We need a bunch of qubits to be the carriers of information, and we need essentially some depth of computation to sort of do things that we could that are interesting, that are beyond the reach of a classical computer. So, for example, these classical algorithms that emerged in the 1990s for factoring, for chemistry, if you sort of sit down and write those in terms of elementary gates, you'll realize quickly that they require a lot of qubits and a lot of gates. But then now, but the promise of them was strong enough that hardware research and building hardware really start to take off. And where we are sort of right now is hardware that exists that anybody can use. Just looking at the progress of hardware in the past 10 years is kind of astonishing, actually, how far it's come. But you might see a big gap. But I still think, it's still a very exciting time to work on quantum computing, and that's for a couple of reasons. One is that so the hardware is basically now at or even beyond the error correction threshold. So there's a threshold beyond which you can do, like if your hardware can get below that threshold in terms of errors, then in principle, what you can do is you can use quantum error correction to essentially bridge that gap. So you can remove errors as they occur in your computation so that they don't accumulate and corrupt the outcome. Unfortunately, the problem with that is that you have to do an encoding and a decoding to get to that error-corrected logical qubits and logical gates, and that overhead of encoding is quite a bit, at least in the early schemes. But still, this promise of quantum applications, coupled with the fact that in principle you can remove errors, just created a boom in quantum computing research to sort of try to see how we can improve this and how we can make progress in bridging this gap. The other reason that it's a very exciting time in quantum is that the hardware that is built right now is basically at or exceeds the types of circuits that you can run on them is basically at the frontier of classical simulation. So you could we're really touching the point where we can run circuits that are large enough that it's very, very, very difficult for a classical simulator to basically simulate. Okay, so taking all of that into context, I mean, then the natural question to ask is, well, beyond those, those earlier earlier original algorithms that were proposed in terms of factoring chemistry, what else can we do? If we have hardware that can beat classical computing, maybe we should search for other applications, other algorithms that are more resource friendly. So there's been a huge amount of progress in quantum algorithms. I mean, by orders of magnitude, researchers in the past decade or so have reduced overhead of running these algorithms, let's say for chemistry. On top of that, there is very active research going on in control of quantum hardware. So in like making better qubits, better coherence, but also better gates, and generally better control that can push the error rates even further and further down. But again, there's a limit to control. I mean, you cannot go all the way down to zero error with just better control. So again, we need new ideas. So error mitigation has emerged as one thing that has been very promising. Zlatko, I know you've had some really seminal papers on this yourself. But basically, error mitigation, the idea there is from noisy data that we can get from experiments, by trading that over with some sampling cost, doing more and more samples, then we can basically remove those errors or mitigate their effect on the output. Again, there are new ideas that are sort of allowing us to bridge this gap further and further. And then lastly, the whole thing, I mean, when we try to write these algorithms and error corrections, et cetera, we're dealing with the language of quantum circuits. And we can build quantum compilers that can kind of automatically transform circuits to other circuits, et cetera. So this is kind of like the broad landscape of
that's a very cool graph. Quick question, Cedric, to you anyway. That picture you showed us from 2017, that was the very first release, the version 0.2?
0.1, I think, it just had one folder called scripts, so I didn't want to show that one. This is the first actual, where it has like quantum circuits, etc.
Yeah. Okay, wonderful. Thank you.
So let's see where we are. Yeah, so I mean, by the way, I should say that this slide is partly motivated by a slide I saw from Ken Brown's talk, Dr. Ken Brown from Duke University. I put my own twist on it, but this is I first saw something like this in his talk. So now sort of if you believe this landscape, then there's a lot, despite the tremendous progress that has been made in both software and hardware. I mean, even just in the past 5 years that I've been involved in IBM, I mean, the progress in hardware and the software and the theory has just been really incredible. But clearly, there are a lot of challenges to building a fully functional large-scale quantum computer. And so the idea behind Qiskit was essentially just create tools that people can educate themselves about quantum. There are a lot of courses that have been built around Qiskit, a lot of educational material, Qiskit textbook, YouTube videos, but also to just give tools to researchers or developers who want to explore and kind of find new ideas, to give them the tools that they need to sort of do their work. So Qiskit at its core is basically just a bunch of tools for working with circuits, with operators and states, with backends, with computational primitives, expectation values, et cetera, et cetera. So that's the core part. This is the Qiskit Terra GitHub repository that I'll be mostly talking about in this talk. But as I said, I mean, the idea behind this is now there are these foundational tools and interfaces, so you can build on top of them to do all the things on applications and error correction and hardware research, et cetera, et cetera. So there's a whole ecosystem of these tools emerging. I'll start with Qiskit Metal. Zlatko has been driving that in terms of basically tools to build and model superconducting circuits for quantum computing. But then there are, if we kind of stay on the hardware side, we want to be able to do, for example, to explore new gates, to explore optimal control. So this package Qiskit Dynamics essentially has a lot of tools to solve Lindblad equation and things like this that you need for doing that type of work. Qiskit Experiments is all about characterizing and calibrating and these things on quantum hardware. I've been excited to see a lot of interfaces being developed to kind of alternative forms of hardware beyond superconducting devices and trapped ions, etc. So there's this package Qiskit called Atom. There's a bosonic Qiskit that was recently developed. So a lot of work there. On the algorithm side, there's a Qiskit Nature, Qiskit Machine Learning, Qiskit Optimization that basically contain algorithms that to solve problems pertinent to those realms. And then there's recently an extension to Qiskit release called Qiskit Quantum Error Correction that basically has codes and decoders and circuits for error correction that you can explore to simulate, etc. And then finally, we talked a lot about error mitigation and things like this. This Qiskit runtime is the idea behind that is that, as I said, for error mitigation and things like this, you essentially need to take a lot of samples, and you need kind of a tight loop between the quantum and classical control. And so the Qiskit runtime is essentially a computational model that sits next to the quantum computer, but couples quantum and classical resources together to do things like error mitigation and other things. Okay, so with that kind of a broad picture out of the way, I wanted to focus the rest of the talk on the compiler, which is sort of essentially circuits and compilers. To me, when I think about compilers, kind of my wish list is that I want these four things. So I want scalability. I want it to be fast. I want it to scale to problem sizes that are going to be interesting for beating classical computing, to do even like things like resource estimation, etc. I want retargetability. Like I want it to be like similar to classical computers, and retargetability means you take a compiler that is able to generate code for multiple different types of instruction sets. So like if you have a PowerPC and if you have an Intel processor, the same compiler is able to basically retarget to different backends. And that's especially relevant for quantum, where you can the gate set and or the connectivity, all of that continuously changes, and new types of backends are available. And so we really want it to be seamlessly retargetable to different kinds of backends. We want pluggability, meaning just this field of quantum compilation is very active. Every day there's basically a new compiler pass, a new method for optimizing circuits, for suppressing errors, etc. It's not realistic for Qiskit to keep up with all of them necessarily, to like put all of those into Qiskit proper. But we do want a kind of a relatively stable interface, such that those external packages can easily plug in to the Qiskit workflow, and people can essentially explore and find, see the trade-offs between the different methods. Abstractability, I don't know if I made up that word or not. I first came up with the 3 words and then I added that one. But the abstractability, by that I mean, I want a compiler that can work in multiple different abstraction levels of a quantum circuit. So when people think of quantum circuits, traditionally in a textbook quantum circuit, it's just a bunch of gates and measurements maybe. But quantum circuits are much more than that, and similar to a multi-level IR for a classical compiler. We want something that can represent the quantum circuit in all the spectrum of different complexities and things like that it can exist in, so that the compiler writers can sort of transform circuits at different stages independently. So maybe I'll start with that abstractability. So here's a chart that I saw somewhere on the internet a few years ago. Basically, so the reason this is relevant is we want to know what a quantum circuit is. As I said, a quantum circuit is much more than a bunch of gates, in my opinion. Maybe others not. But I like this chart because it's sort of, it has this different spectrums of where you fall in what you believe is a sandwich. So if you're a purist, in terms of, there are two axes that one is what's the structure of this thing, and the other is what are the ingredients. So, if you're a purist, you say, the structure must be that it has bread at the bottom and top, and it has like some relatively traditional things in the middle, the ingredients. But then you can start to get, more adventurous, and you can say, maybe a hot dog is a sandwich, maybe an ice cream sandwich is a sandwich, maybe a Pop-Tart is a sandwich. So I'm curious, Zlatko, where you fall in the spectrum.
I'm doing some soul searching right now. Yeah, folks, feel free to reply in the chat where you fall in the spectrum while I also digest this. I don't know. I'm gonna middle leaning towards the bottom right corner. I'm gonna go extreme here, but it depends. It depends on yeah. I don't know. I have to think about it.
Okay, yeah, I'd be curious. We should take a poll. But okay, so then based on this, I thought, let's make a similar thing for circuits. Because this was a real debate in the team a few years ago of like, what are we calling a circuit? So as I said, you could say like the traditional circuit is like a quantum Fourier transform is a circuit. Okay. But then you might say, all right, I want to put in my circuit things of like different abstraction levels. So like higher level functions, maybe. So like I say, do a bunch of Hadamards, and then do a Boolean function, where this function is really just literally a classical function that you could even pass to your Python interpreter, and it just interprets it. But it's a classical function. But any classical function can also be converted to a quantum circuit. So I want my circuit to be able to represent these kind of things. Or you could go even further down. You could say, these gates are essentially discrete time dynamics of quantum states. But maybe I care about continuous time dynamics. Maybe I care about pulses. Maybe I care about delays and things, timing and things like this. And again, like for specific types of circuits that I'm writing, maybe like I'm characterizing my device, those become really important. And I want to be able to write circuits that are flexible enough that can represent these kind of things. On the other axis, we start to think about, mixing with the quantum unitaries and quantum evolutions, a little bit of classical control. So, you could have some simple classical control. This is the type that existed in OpenQASM 2 language to represent things like, measure some qubits, and just based on whether they're 0, 1, communicate that measurement result, and then like condition a particular gate. If it was 0, apply it. If it was 1, don't apply it, let's say. And with that, you can like things like teleportation. Or you could sort of kind of go crazy with the classical control. So you can assume that you have a full Turing machine, a Turing complete machine next to the quantum processor, where you can measure your qubits, and then you have a bunch of classical bits, and then you can apply any function, even maybe a very difficult function on them. But because you have a classical controller sitting next to the quantum core, it essentially is able to do any classical computation. So things like maybe like this example of a logical T-gate teleportation, you want to measure a bunch of bits and then do a majority vote. So that's a simple function, but still, you have to write a fully classical function over them. And so this is the spectrum of quantum circuits. And so I think in Qiskit, basically we're down here. We want to be able to represent all of these things, and we want to be able to write compilers for all of these things. And I think they all have some interesting use cases. I was not able to quickly come up with use cases for these, but I think if you think hard enough, there are probably use cases. Okay, so
I'll just feed you some comments quick. Dr. Kellyanne, she said she's a radical sandwich anarchy is the only correct choice. So I think, people are steering towards that corner, like you said, and yet somebody else said the ice cream sandwich. So a lot of rebels here, a lot of anarchists and rebels in this chat.
Okay, good to hear. So we had a good crowd. All right, so on the abstractability, so instead of just talking, I thought, I would just show some code in Qiskit. So do you see my Jupyter notebook?
Right.
Yes? Sorry.
Yes.
Okay, so this is just a notebook to illustrate this idea of circuits at different levels of abstraction and also mixing classical with quantum. So okay, so let's say this is not necessarily a useful application that I'm building, but just a random circuit to just illustrate. So let's say I start with a 9-qubit circuit. I'm just going to put a unitary on it. Like I have a matrix. I just dump the matrix on 2 wires and call that, now that's my matrix. Then I have, then I'm going to say that Boolean expression that I showed. You can actually just do that in Qiskit. You can create this Boolean expression, put anything you want here, any Boolean expression here, and then just put that on the circuit. It's the compiler's problem now how to deal with this, how to synthesize this. You can do.
That's pretty cool.
Yeah, so you can do similar things like get phase oracle. Like you're telling essentially the compiler, take this Boolean expression, but then like synthesize it as a diagonal for me, where the diagonal job is if the expression of value is to true, put a phase on the computational basis. If not, don't do anything. Then you can do other things. Like maybe you want to put a Clifford. Maybe like this comes up in randomized benchmarking, for example. You want to put a Clifford on your circuit. So you just, if you just describe your Clifford, you don't have to know a decomposition for it. You just put your Clifford on the circuit. Going further down, maybe you want to have like some time evolution by some Pauli. Okay, so you have this object Pauli evolution gate. You define your operator, and then basically you just say, e to the I that, and then you just put it on the circuit. Again, that's the compiler's job to decompose that. And then, of course, many people just want to write circuits at the abstraction level of gates. So you just put like a bunch of CNOS and Hadamars and swaps, etc. This is that classical control that I talked about. So maybe you want to have something where you have like a while loop. So this is consistently just measuring a qubit, and it stays in the while loop while that qubit is I think 1. If it's if it's a 0. If the moment it reads out a 1, it terminates and it jumps up. So this is that there needs to be a very tight coupling when you actually go to execute this between the quantum and classical processors that are sitting next to each other.
Just slow you down for a second for folks to follow. So the block that says while loop in the diagram above, that's going to have all the code that's inside of that.
Yes, it has. Yep, exactly. It has reset Hadamard measure. So this just keeps doing this. Reset Hadamard measure here. And it only exists as box when that value is to 1. Yeah.
Great.
And then, going down in the abstraction levels, I talked about, sometimes we just want to like work at the level of pulses, right? Like maybe I have my own favorite X gate that I calibrate. I call that my pi pulse. It's a new pulse that was never in the library of Qiskit, but I just teach it. Like I teach Qiskit that is equivalent to this pulse, this Gaussian pulse. So like if I expand the definition, it's saying like on some channel with some amplitude and some standard deviation, do a Gaussian pulse. And so that now is the definition of that pi pulse. So then I can grab that and just like a regular gate, just stick it into the circuit. And maybe I do a bunch of delays around on other qubits, just because because I want to delay. So the point is you can also you're essentially putting some constraints on the circuit to tell the compiler, whatever you do, however you compile this, make sure you have a delay here, because that's important to me. Okay, so let's just look at this circuit. I mean, this is a circuit that I described at different levels of abstraction with different kinds of control flow. And then the compiler has to be able to handle this. So then I just say, transpile. This is the command for circuit rewriting in Qiskit. And then I say, like, I want to rewrite this in this basis, let's say. And so this is what it does. So the compiler obliges and it outputs this. Okay. But one point I wanted to make was that this thing about having different levels of abstraction in the circuit and in the compiler, it just goes beyond just the philosophical thing. There are real advantages, like in terms of just optimization of circuits in it. So for example, the one thing I wanted to illustrate here, just for illustration purposes, is that say I have this ladder of CNOTs and and swaps. So that's just about so there's a nice structure there, right? Like this whole block is a is a classical function because it's just a bunch of classical gates, and it's in fact a linear function. So what we can do is tell Qiskit, tell the Qiskit compiler, go and collect linear functions that you can see in the circuit. So we'll go and find this whole block, and then, sorry, let me find it.
Ali, could you increase the zoom level a tiny bit on the, yeah, that's a little bit better. Thank you.
You see it? Okay.
Yes.
So I write this pass called collect linear functions, and I just say, I make a pass manager, which is like this, the pipeline of compiler passes that are running on my circuit. And I say, run that collect linear functions on this circuit. So it goes and it finds that whole thing and it calls it a linear function. So now because the circuit is able to represent higher order things like linear functions, we can just now collapse that whole thing into what I called it lifted circuit. I lift it up into abstraction level. Okay. Now, because that has a nice structure, there are known methods. There's a lot of research on synthesizing linear functions, for example. So now I can go and take this and resynthesize it into something with hopefully a better cost. So for example, I get this, which has a much lower depth. It's a very parallelized version of what we had above. So what we had above was this ladder structure. If you expand these swaps into 3 phenos, it has a long depth. It's very serial. So we can basically, here I use the pass from an external package, actually. So I'll talk more about this in the pluggability of the compiler. But there's this software called Tweedledum, which has a bunch of compiler passes actually inside it. So here within Qiskit, I'm able to call out to that. So it has, in particular, it has this method for stat synthesis of linear functions. So I just write a dummy small pass around that to just call Tweedledum's function, and then get a synthesis for this. And then I can basically take that serial implementation of the linear function that I had and convert it into a very parallel implementation, which has lower depth. So this was just on the abstractability of circuits. So, I mean, there's real benefit in being able to play with these different abstraction levels, not just for ease of programming, which is really important, but also just for optimization purposes. Okay.
Question. So if I have a GHZ circuit where there's one Hadamard, which is kind of, let's say, the quantum piece, and then there's a bunch of C naughts that look pretty classical, and I think that's a linear function, right?
Yes.
Right. If I then want to transpile that onto some topology, like the heavy hats in a larger set, this would kind of figure out exactly how to do that in the optimal way and minimize the depth and parallelize it, I guess.
Yes, exactly. So this particular function exactly does that. It finds the optimal depth for that implementation. But because it's SAT solving, it's not particularly scalable. So here I have a 9-qubit circuit, is fine. If you try to do like a 50-qubit circuit, maybe it struggles. So then we have to rely on other algorithms that are heuristic. But yes, that's the idea behind this method.
Okay. Thanks, Ali.
Yep. Okay, so let me go back to the slides. So we talked about these sandwiches and circuits and abstractions. The second piece of this is, as I said, we really want a compiler that is scalable. So in the ideal world, you should not really notice a compiler. Like if your job is not compiler research and compiler engineering, the compiler should just exist. I mean, it should just make your life better, but you shouldn't notice that it exists. It should not take up your life from your work. And so we essentially want compilers that are fast, and also that can scale to problems that are that as I showed in the first chart, we can have many different large circuits. And so even if we can't execute them today, at least we want to be able to do resource estimation on those circuits. Okay, so Qiskit started as a purely Python package. And that was kind of nice for prototyping, getting a lot of contributors and people just having a very low barrier of entry. But then as it grew, yes.
Before I let you go on to the next section, maybe I just don't want to miss this question from Charles Robinson before we get too far about corner cases or edge cases and accuracy. I think he means either for the linear function or just for the transpiler in general. Maybe if you just want to comment on edge cases and accuracy and all of this.
So linear, maybe, I mean, maybe I don't understand really what edge cases means here, but I mean, there are several issues. So one is like the objectable optimization they want to do. So you want to optimize for depth or size. Like those are two different optimizations, and typically there's a trade-off between them. So the more you optimize the depth, you lose on size. And by size, I just mean number of gates. And then so scalability of it is one issue. So like if for small cases we have optimal solutions. If you get larger, then I mean there are methods that can, I mean there are scalable methods. If you also want to couple that with a limited topology, like Zlatko mentioned as heavy hex or whatever other topology, then it becomes a slightly harder problem. But still, I think it's not a terribly hard problem. It definitely still methods can be improved. But I think we do have some methods for essentially solving this in a general case. I don't think there are particular edge cases in this one, at least. Okay.
Thank you.
Yep. So scalability is, as I mentioned, is something that we kind of care about. And so in recent releases of Qiskit, there's been a lot of push to get performance critical parts of Qiskit into compiled languages such as Rust. Actually, this was an effort that different people contributed to. It was led by Matthew Trenish. But now, I mean, there's been just a staggering progress in the performance of the compiler. So I just wanted to illustrate a few of these. So let's say I have a huge quantum computer. This is actually a heavy hex topology to run a distance 21, I think, surface code. Sorry, heavy hex code. So it actually has 1,000 plus qubits. Okay. So again, these examples that I'm showing are kind of artificial, but just to illustrate something. So suppose I want to run a quantum Fourier transforms on this. Okay, you would not do this if you don't in a non-error corrected setting, but just to show that the software can handle it, right? So I'm just going to build a bunch of QFTs of larger and larger sizes and then run them, and then basically it's a full transpilation pipeline. So I take the quantum Fourier transform, I compile it to that coupling map and the basis gates that the device has, which are like everything should be in the end in terms of C naught, square root of x, so x90, and then R0 rotations. And then so as you can see, as you go to bigger and bigger number of qubits, of course it slows down, but at first it's very fast, like 1 or 2 seconds to up to even 100 qubits is less than 5 seconds, around 5 seconds. And then yeah, I mean it goes up. But these are really huge circuits. I mean, like you're taking a Fourier transform, which has very demanding connectivity. So it's a very challenging routing problem to actually map that to a device like this. So like one of those like 10 qubit circuits you can see even is quite a large circuit. But again, I mean, these are, it takes time. I mean, there's probably more room for improvement, but still it's much faster. And maybe I can illustrate a little bit. So this is a graph. So this other compiler Qiskit, which is actually I think one of the better really good compilers out there. So we benchmarked Qiskit's latest release against Qiskit. So this is performance in terms of for two types of circuits. One is quantum volume. One is quantum Fourier transform. Sorry, my labels are misplaced. This one is quantum volume. This one is quantum Fourier transform. The red line is parity of performance. And then this one, anything above the red line is Qiskit faster. And so you can see that Qiskit is about a 1.5 order of magnitude faster in terms of compiling these large circuits. So there's definitely still room for improvement, but I mean, yeah, so there's been great progress in terms of porting the parts of the compiler into Rust, but also parallelizing and multi-threading. That has helped it quite a bit as well. Okay, so the next part of my talk, if there are no questions.
There is one quick question, and maybe this may be a good segue to the next one, which is, what about hardware-aware compilation optimization, optimizing with respect to fidelities, qubits, decoherence?
This is a great segue into the next part. Yeah. So basically this retargetability that I talked about is where I have a circuit that was produced from maybe some higher level application or something, and then I want to retarget it to different types of backends. And a backend is essentially in Qiskit is now characterized by an object that is literally called a target. And a target just basically communicates to the compiler what are the constraints, what are the features, what it has, what it doesn't have. And then the compiler has to basically make the best use of that and generate code for that target. So that includes connectivity of the qubits, what gates does it support, what are the error characteristics of those gates. So this is the hardware error piece of this, right? So what are the durations of each of the gates, or what are the errors of each of the gates. And then maybe in advanced versions, the compiler has to be aware of like what capabilities does it have. Like, can I do a mid-circuit measurement or not, for example? So okay, let me just go
on the real-time side of it. We had, with the quantum side, you have notions of basis gates and so on. But I wonder with the transpiler having to take these arbitrary classical functions and,
Yes.
compile them onto some kind of real-time controller. What does the compiler need to know about that? The transpiler.
Yeah, I mean, this is kind of sweeping a lot under the rug. So in a real setting, you need to know a lot about the backend. Like if you're generating real code for the backend, so Qiskit is not generating actual binaries for the backend, right? It's generating a circuit that is compatible with just the general constraints of the backend, like the gate set and things like this. And it's trying to make, like, if there are good gates, try to use that more, for example, things like this. But then when you actually want to take that circuit and create a binary that for the classical controller that will actually run the quantum computer, then that's a whole different problem of essentially classical code generation. Like you basically want to be able to know an intimate detail about the controller, the different like memory layout, et cetera, that is not exposed to Qiskit at this point. And that's definitely, I think, an interesting. We have started talking about these things. I've like communicating constraints and things like that. But definitely, yeah, there's a lot of details that maybe is not captured here. Okay.
Thank you.
Yep. So retargetability. Is this visible? Yep. Okay.
Yep.
So for this demo, I'm just taking a quantum volume circuit, and quantum volume circuit is just a bunch of 2-qubit operators, SU4s, applied to arbitrary pairs of qubits. Okay, it's a benchmarking technique. But I just want to show, like, if I change the target of my backend, how the compilation changes. So first, I'm just going to take this circuit that is on virtual qubits and map it to physical hardware by saying, like, I have a line of 4, let's say. So the compiler will take this and map it such that those SU4s are now applied on physical qubits, and then with a bunch of swap overhead, obviously, because the original circuit was not perfectly matching the hardware. Okay, so now starting with this circuit, now I want to decompose these SU4s. But the key thing here is that I know which qubits the SU4s are being applied to. So like this one is being applied to physical qubit 0, physical qubit 1. This one is being applied to physical qubit 1 and physical qubit 2. And so those physical qubits and the gates that exist on them have certain characteristics that the hardware can communicate, right? It can say, like, I have a C0 here. Maybe I have a CZ here. Maybe like this C0 is very good. Maybe the CZ is very bad. I don't know. Like, it can communicate these things. So this is one example of a target in Qiskit. So you start with a target. And then this one, I'm just saying, like, assuming that it has calibrations of like a standard IBM quantum hardware, which is a square root of an X gate, an RZ gate of arbitrary angles, and a C0 gate. And these are like which qubits they exist on, and then like what is the duration, what is the error for each of these instructions. Okay, so this is all the instructions that the hardware understands. So that circuit has to be transformed to something over this instruction set.
Is the duration only used in a scheduler, or is it also part of the error estimate and optimization?
Yeah, that's a good question. Right now, it is ignored by the error model. Only this part is chosen. But yeah, you can definitely like imagine where some some future where you're taking into account like the coherence or the relaxation times of the qubits and saying like, I want to minimize duration as well, right? Right now, it's not. It's used by the scheduler right now.
Yeah, gotcha. Thanks.
Yep. Okay, so I'm going to make this target, and then I'm going to say transpiler synthesize for me. So I just made a utility function at the top, doesn't matter. So what happens is that quantum volume circuits becomes this. So it becomes a bunch of, z square root of x rotations, a bunch of c naughts, and exactly what the target expected me, right? Now let's say I calibrate a new gate. Let's say instead of having only the 90-degree rotation about the x-axis, I'm going to essentially make a pulse that by just changing the parameter of the pulse, it gives me any angle rotation about the x-axis. And as I associate a certain error model based on what I measure, benchmark that gate, I associate an error model to that. And then I also calibrate the new entangling gate. Just for fun, I'm going to assume I calibrated a controlled Hadamard, okay? Which is like much better in terms of error compared to my C naught, okay? So I want to see if the transpile, so this is now added to the previous target. It's not a replacement. So it's like an over-complete basis where the compiler has to basically find the best configuration of gates to use. So I'm just adding these new instructions that I've calibrated.
And then, wait, quick question. So the presumably the depending on how that Rx of theta is implemented, the error would depend on the angle theta. Does that go in the model?
Here, because I'm just adding like all the thetas with one property, so it's assumed that they're all the same. But if you want to have like different angles having different errors, you can do that. I'll show next. There's an example of that.
I see. Okay, very cool. Yeah. Thanks.
So here, when I recompile, now I see that the compiler is preferring to use a continuous rotation of x rather than two x90s because like it's just more cost effective. But also notice that it's like it has the choice of using an xzx or zxz, but because z gates are just basically very cheap, it's preferring zxz, right? Like it's smart in terms of knowing what decomposition is best, and it's also preferring to use these controlled Hadamars that I calibrated newly. Okay, so then now let's just add more gates. Maybe I calibrate RZZ gates. So rotation is about the ZZ axis with some discrete angles now. So like I have a theta 1 and theta 2 that I calibrated. Let's look at this. So I'm just randomly picking an angle. Like I'm picking a 18-degree rotation and a 45-degree rotation. I'm just going to add these. So that 18-degree rotation is like a pi on 10 rotation, and this one is a pi on 4 rotation. And so
quick question. Are the results here deterministic or stochastic?
These are deterministic. It's basically the decomposition and associating cost to it.
Oh, okay, right. So it's deterministic, and is it optimal for the given cost function, or is it a local?
Yeah, it's a good question. So for these, I mean, I need to talk a little bit about what gates it can target right now. So right now it looks like it can do anything, but in fact there are certain families of gates that it can target. So for these families of fractional, so this family is essentially fractional controlled gates. So like you can have like fractional CNOTs, fractional ZZs, fractional XXs, whatever, for like discrete ones. So for that, it's optimal. I can put the reference somewhere. But yeah, so
that's this paper that you had on the archive recently.
Right.
Yes.
But for the other one, when it's decomposing in terms of controlled Hadamars, so this again, also the decomposer that's been used here is essentially any super controlled gate, like a B gate, for example. Like if you calibrate a B gate, it can use it, but it won't be optimal. So that needs some work still to become optimal. But yeah, so I have a little picture at the end which shows sort of like what gates are supported. And then so now I calibrate these fractional ZZ rotations. And the controlled Hadamard still exists. So the controlled Hadamard is still used in some places where it's more cost effective, but now in some other places like a ZZ pi over 10 or ZZ pi over 4 is used. Okay, so this is just like the compiler being able to use gates as they get calibrated and sort of try to do the best it can. But then also, just suppose I throw away the superconducting quantum computer and I buy a trapped ion quantum computer. So that has totally different gate set, right? So like I'm starting a new target, and this one has like R gate, which is like this 2-parameter rotation gate, single qubit gate. And then maybe I calibrate these XX gates using my Wolmer-Sorensen interaction, whatever. Like I have an XX90, XX45, let's say. So I build this whole new target. Again, the same circuit can be rewritten in terms of in that basis. Okay, so yeah, so different computer architectures have different types of native gates. Even within the same architecture, you can sort of play with the calibrations and maybe come up with that clever techniques. And we really want the compiler to be ready to use that. Which bases are supported is maybe ignore this for single qubit one for now, because this has some it takes a while to explain this one. This is not maybe very illustrative. But for the 2-qubit case, essentially, if you give the compiler any gate calibration, basis calibration from this green line, this is called the supercontrolled gates. It can support a single one of those, and it's non-optimal, or it can use multiple of these controlled ones, or even a continuous one, like all angles of RZZ, let's say. And this is optimal. So control gates and supercontrol gates. So like if you have a C0, that's good. If you have a B gate, it can be decomposed. If I swap is fine. A square root of a C0 is fine. We can generate code for all of these. But let's say if you have like a square root of a swap, well, not yet. Or like if you have XY interactions on this line, not yet. But those are all, I would say these are really good avenues for contribution to the Qiskit compiler to be able to support more richer gate sets.
And so the swap being at the top there, that means it's the hardest to do for anything that's on the bottom of the vial chamber, I guess. And you can't like shortcut it in any way. Is that with fractional gates? Is that
yeah? Swap is exactly. Swap is the hardest.
I see. But anything below the swap, you can maybe using fractional gates get away. So if I had a generally maybe 3 C0s to implement a general SU4, but here with fractional gates, I can end up with an effectively shorter pulse.
Exactly. Yes. The idea is that you're basically making some rotations in Hilbert space to get to that target. And so if you don't need the full rotations, maybe you can get away with finer rotations, then you just use those if they're more cost effective. If they're not, if the smaller angles have the same error, there's no point. But if they have, typically they're shorter and so higher fidelity. So.
Awesome. Thanks, Ali.
Yep. Okay, so lastly, pluggability. So as you might have inferred by now, a quantum circuit compiler is basically a staged series of transformations of taking an input circuit and doing basically like different like basis rewritings and routing of qubits and unitary synthesis, et cetera, combining gates, merging gates, canceling gates, commuting gates, all these things. And so, Qiskit comes with preset pass managers where you can just, use them out of the box and not think about it. But if you really want like ultimate performance, or maybe if you're doing research, then you can think about plugging into specific parts of this. And so you don't want to make the whole thing from scratch. So this pluggability is again something that was added recently to Qiskit. And the idea there is, so there's this plugin interface where you can, let's say you're a student that did some research and wrote a nice paper on circuit optimization. What you can do is Qiskit advertises this interface for pluggability. So you can package up your code and put it on GitHub and PyPy. And so users can essentially do pip install of your code. So your code doesn't have to do anything with Qiskit. Like it's not in Qiskit. Qiskit doesn't know anything about it. But a user who installs your code with the right interface, then you can Qiskit will discover it. It will discover it based on the install packages, and be able and essentially plug it into the Transpile pipeline so that you can actually use it. So for example, these are the routing methods that exist as plugins. So some of them are in Qiskit, like these ones are in Qiskit. This one is a recent one that actually the paper on this is not published. This is from the IBM Dublin team. But it's a alternative routing method, which is not in Qiskit, but I just pip installed it, and it's now discoverable within my Qiskit environment. So let's say I make a Quantifier transform circuit, and I want to see how it performs under these different routings. So it's the whole thing is as simple. So this is the Quantifier circuit. The whole thing is as easy as just changing this argument of Transpile. So like if I say use the Saber method, I get this. You see the swaps that got inserted. So there's some depth and size now associated with the circuit. Now I said, now use the stochastic method, I get this. Use the look ahead method, get this. And then this new one, after I've installed it, it's available just like any of the other ones because it advertises that I'm a routing method for Qiskit. And so if I now say this DSM method, doubly stochastic matrix based method, it's now this one, right? So you can play with these things, and so it's kind of a necessary part of a software package like that is, it's also a field that is very fast moving forward. There's just a lot of methods, and it's not realistic to put all of them into Qiskit. And so the pluggability is kind of a very nice way of making things plug and play with the rest of Qiskit, so that any end user can use your package. Okay, that's all I want to talk about. I think I went over time maybe a little bit, but I'm happy to take any questions.
No, you're amazingly just 1 minute over. Usually we have folks finishing 15 minutes over. So congratulations, that's a special gold star, especially with my long introduction today. Folks, this is a great time to post your questions and in the comment chat box here on YouTube. It's also a great time to float up any questions that I missed during Ali's presentation, and to take and to let us know all of the various things that we might have missed. And sorry, I'm trying to read the questions here as we have them coming in. Maybe the first one is from Shashi Kumar. Will these notebooks be used during your talk, be made available? In other words, can somebody go and look at these notebooks after?
Yes, I'll make them available. It's just, so I should warn that part of what I showed is not in the latest release. It'll be in the next release. So if you're just if you're just installing pip install, you won't have access to it until the next release. If you're using it from master, you can. But anyway, I will put the slides somewhere, and maybe in the YouTube description we can add it. I don't know, later.
The notebooks, yeah, we can add them. Maybe Clinton can help us update the description. And by the way, Ali, you've just demonstrated two of the core features of the seminar in the spirit: the open science and open source, of both Qiskit and the demonstrations notebooks, so anyone can go and learn this from all over the world. And the second one is that it's all leading edge research here. You can't pip install this yet. You have to be on the development branch. So I like that very much. We're keeping it fresh as usual. And the second part of it was, I think, about GPU optimizers, or how does that potentially factor into the compilers and so on.
So GPU optimization?
Yes, can you use, so I think, if I understand the question, and feel free to elaborate in the chat, is what about GPUs for supporting and optimization in compilers? I think if everything so far uses the CPUs, but what if we use some of these special purpose accelerators?
Yeah, everything that I showed is using a CPU. Nothing here uses GPU. I actually it's an interesting question. I don't know. Maybe I think if somebody is able to demonstrate that would be very nice. Like taking one of these passes some of these passes, I mean, like, to solve them in an optimal way is just a hard problem by nature. And so, on large problem scales, they can take a long time. So if somebody is able to demonstrate that they're faster using GPU, then I'll be very interested in seeing that result. Yeah.
Excellent, thank you. And Shashi, just to make a comment, this problem is different from the problem with simulating the wave function and using tensor products and tensor networks and all of that stuff. Those are two different problems. So I think your question maybe alluded to that as well. That's a separate part of Qiskit. Next question, is circuit optimization being driven by cost optimization? Trying to understand the functionality of the cost to quantum solution. I think it's a question about what is the cost optimization in all of these many different passes, and how do you even arrange the passes?
So cost might mean two things. I don't know which one you mean. Like, is it so okay, so there's a cost function within the compiler, which I mean, I alluded to a little bit, which is like, typically you care about the depth of a circuit or a number of gates in a circuit. In these more hardware-aware passes, you care about not just depth, but like the fidelity of the circuit. Like you have some error model, so you want to optimize for that. So like every compiler has some cost that it's trying to optimize for. Among some options is like picking the best one. So like those routing methods that I showed, like we know swaps are like an expensive gate to do. So expensive meaning like they're lossy, they introduce a lot of error. So like I want to minimize swaps, let's say, or depth of swaps. So there's a cost within like the compiler architecture that is being considered. I guess maybe the other interpretation of your question was like, what does it mean for like the cost of quantum computing in general, like trying to optimize these circuits? I don't know if if I understood correctly, but if that's what you mean, like, I think generally like the whole point of compilation for these near-term devices at least, but also for future fault-tolerant devices, is that that first slide that I showed, that we're trying to like make things work, right? Like there's a certain reality of the hardware with some errors and loss. And then there are things that we want to do that are sort of out there in terms of resource requirements. And the compiler's job is to sort of try to bridge this gap, right? Try to do circuit transformations in such a way that, let's say, errors don't accumulate as much, or maybe like in some circuit transformation passes, like you can save some qubits, let's say, or something. So that's it's about like making things that were hard to do more feasible on the actual hardware.
Mm-hmm. Awesome. Then there was a question about if the compiler works for superconducting qubits only or beyond that. Although I feel like you answered that question by showing some of the ion traps, but maybe you want to elaborate a little bit more on what has actually been used. Has it been used in practice?
Yeah. So no, I mean it's not only for superconducting devices. It depends. I mean, as long as if the backend has a basis set, instruction set that fits that what I showed in that kind of a pyramid. It's like it has a family of gates that is within that family. Then absolutely Qiskit can just generate code for it and optimize over it. But if you have some other exotic hardware, I don't know, like for example, I showed in the beginning like bosonic Qiskit, right? Okay, so that's just kind of different. I mean, like just the circuits look different in there, and so a lot of this is research. I mean, I kind of showed what is there today, but trying to optimize like bosonic circuits, it's an interesting research problem. Or like other things, like I don't know, maybe somebody has a different architecture that where the interactions are different. So definitely the breadth of architectures for quantum computing is very large. But for a large part of them, I mean, like if you have these, essentially, we know that 1 qubit and 2 qubit gates are universal for quantum computing. And so Qiskit's optimizations of 1 qubit and 2 qubit operators is actually very good. So if you can express your circuit in terms of 1 qubit and 2 qubit operators, Qiskit likely has some method for translating between the bases that you have. But again, it's not a definite statement.
Interesting question. I literally had a discussion with someone about this today, but Ali, feel free to elaborate here. Can one plug in a custom target, such as, say, a superconducting circuit designed from Qiskit metal with simulated Hamiltonian parameters?
Yeah, can you characterize the unitary of it? If so, yes, it's fine. Like you can say, yeah, you just calibrate a gate. Qiskit necessarily doesn't need to know the calibration, but like you advertise in the target that like I have gate foo that implements such unitary. Like if you can do tomography or something on your gate and find like the closest unitary that it that it's implementing, then it's likely that Qiskit will be able to find a way around it. So like even that, okay, so those lines that I showed, of like, you don't exactly have to be on them. Also, if you're epsilon close, it's fine. Like Qiskit can probably find some decomposition by using some close gates. Anyway, so that I hope that answered the question.
Yeah, that's wonderful. Thank you, Ali. I can also add a little bit from the Qiskit Metal bottom-up side that, yeah, so Qiskit Metal right now will simulate the hardware all the way, if you want, from circuit elements like inductors, capacitors, even the layout. It can then give you the full Hamiltonian without any approximations, which you can then even feed into Qiskit Dynamics, which is one of the latest packages to be added to Qiskit. It can also provide you like the effect of qubit frequencies and harmonicities, J couplings and all of that, which you can then use as a model to feed into the next level of a simulator. And then I think we were discussing actually a more explicit potential connection to the higher level abstraction, because here a lot of what Ali showed was really at the level of a higher abstraction, but connecting that stack is really interesting. Great. Okay, so if I missed your question, please repost it now. Otherwise, I'll give Ali a couple of minutes here to share any final words and thoughts with us. And I'll also remind everyone on the video call that if you applied to the raffle and Ali and I are lucky to get to hang out with you after this and have a fireside chat, you should have received an email with the WebEx link that you can log into. You don't need to install the WebEx. You can just use the web version. So this is a great time to check your email, and Ali and I will be on that WebEx link right after the seminar ends. So Ali, any final words to share with us here?
No, thank you. Thank you for the opportunity to talk, and it was fun. Thanks.
Yeah, thank you so much, Ali. It's been really our pleasure. I'll share with you that we have a lot of positive comments from folks in the chat, and I can't even get to all of them now. But Teddy, for instance, says number 100 was great live. Thank you so much. And really, with that, folks, I'd like to thank you so much for being part of our 100th Qiskit seminar. That is a lot of hours. That's way more than 100 hours of work for everyone here on the team and myself that have put in. So big, huge round of pats on the back to everyone who's helped contribute and make this success and really helpful to the community. Thank you, Ali, for being our celebrity today and 100th seminar speaker. And to everyone who joined us in the raffle winners after this, we're really excited to see you there. And folks, otherwise, I look forward to seeing you next Friday at noon Eastern Time. Okay. Thank you very much.